All right. Let me just glance at the other problems there and see if there's another one that we need to do before we go forward. I think you've got a sense of how to handle these. I'd better do another one. Yep. Here's one. This is like a valve type of or plunger that moves only vertically. And then we've got this rolling arm down below here. And what we want to do is determine the acceleration of this shaft, B here. And it's got a spring in there to keep it pressed down against this arm. So we want to find the acceleration of this shaft B when theta is 60 degrees, measured off the left-sided horizontal. And there's an angular acceleration to this arm of 8 radians per second squared. And there's a particular angular velocity when theta is 60 degrees. Okay. We're looking for that vertical acceleration. I'll just draw the surface here. Just make it a side view. "60 degrees was off of the horizontal. So it's got a 60-degree angle for theta. We've got some geometry given to us on this. And then this is B, and it's forced to move vertical, and we're looking for the acceleration of B. And we're given that theta dot is what?
4 radians per second.
4?
Yeah.
Thank you.
And theta double dot is 8 radians per second squared. And that's in the same direction as theta.
Okay. Both positive,
Yes.
given this sense of theta. Okay. And the arm?
Is 80 millimeters.
0.08 meters. And the...
Is 20 millimeters.
You know what I'm going to do? Let's go ahead and keep it in millimeters. Are we doing any... are we involving G in this problem at all? No, so we're not involving G, so I think it's just a geometric type of consideration. So let's just stick with the 80 on the millimeters and the radius again. 20 here. Okay, good. So we need a geometric relationship. Yeah. Mm-hmm. Okay. So at least what a couple of people were saying out loud there is it looks like we need this defined off of this reference plane. I guess we could call that y. And it looks like y is equal to given theta in here. Why don't you write down without saying it out loud what y is? At distance y, okay, you should have it. 80 sine theta to gets us to the center of the rotating disk, and then add 20 to that. 80 sine theta plus 20. Pretty straightforward. Okay. So then we just start differentiating this, and I think what we're looking for here is the y double dot. Y double dot. Okay. So y dot is 80 theta dot cosine theta y double dot is the acceleration of b that we're looking for. So that's going to be 80 theta double dot cosine theta minus 80, I'm going to write it underneath here, minus 80 theta dot squared sine theta, because again we're differentiating with respect to time. When you have functions of theta in your original description and you're shooting for accelerations, be aware you're usually going to end up with an alpha term and you're going to end up with a square of the omega. But you hear that? Okay. Just words of caution, because sometimes when you're differentiating you'll forget one of those terms. So be careful there. And I think at this point all we have to do is drop in the numbers. Okay. So the AB value should be 80 times the given alpha, 8 cosine of 60 degrees is a half, minus our 80 times our 4 squared, and our sine of 60 degrees is radical 3 over 2. This is 320. This is millimeters per second squared now. And then over on this side we have 64. Let's see, that's 640. Square root of 3.
That means it's actually accelerating down.
It's got to be something positive.
Looks like this is coming out negative, doesn't it?
I got positive.
I got
It should be positive too. Well,
no, it should be negative because when it's coming up, that means it's bringing that plunger to a stop.
Right, but it's also slowing down. It's going up, but it's slowing down.
Right, so the acceleration is going to be negative because it's slowing that plunger down.
Right.
Because there's that spring there keeping the contact.
It's going to be slowing the plunger down.
Okay.
Yeah.
Are we in agreement
Yes.
with
Yes.
what you guys were saying?
Yes.
Okay. So we're noticing a negative value. I'm really glad you folks are pondering the values we're getting, because that's what I've been trying to get you to do all term, is ponder always at each step of the way. Think about the values you're picking up of the different components. That's why I like to keep these separate instead of just turning on a calculator and pulling them up. And so anyway, we end up with a negative what?
788.5
Got that too.
millimeters.
Negative 70.
788.5.
Yeah.
Thank you.
780 millimeters per second squared.
Millimeters per second squared.
Cool.
Okay.
But R didn't really matter at all. Little r. Little radius.
Yeah, it did.
Uh-huh.
Oh wait.
20.
Well,
No,
Well-
it's a derivative though. So it
It's
doesn't matter.
just an offset.
it's a physical offset is all. Yeah. So we could have just put this arm right up against that.
Right.
Yeah.
Wondering to myself.
Now, here's where we could go with this very easily. We could ask you what this little disc is doing at different orientations and different parameters here. Okay? So we could ask you what the rotational rate is, maybe the omega of that number, that kind of a thing. Okay?
Considering the plate is moving above it, it's just rotating at a constant rate, isn't it, for that section? Because the plate is moving up and down.
Well, does this have an alpha? Does that little disk have an alpha?
I don't think so.
Does it have it's obviously got an omega if it's not slipping. It's rolling. It's rolling.
Because
Yeah.
the arm is rotating at a constant rate.
No, it's not.
No.
It's got-
Oh, never mind.
Yeah.
It doesn't have alpha.
It's not. Okay. So it'd be pretty easy to ask that question. Okay. Okay. So just, okay. Let's see. I think it might be worthwhile. Oh, I should get started on velocity. I better move on to the next material. I may come back to at the next class session and do another one with you. But I think I want to go ahead and move on. So let's now move into the vector approach to handling relative velocities on a rigid body. Relative velocity on a rigid body. We had a brief introduction to relative motion earlier in the course, and now we're on a rigid body though. So here's the way we can do this, is if we have some body and we have a described axis system, reference non-moving inertial type of reference frame, we could take 2 points that exist on this body and we could label one of them A, one of them B. And we could write position vectors to each of those points. So we have a position vector to get us over here to A, and we have a position vector to get us to location B. Now what else could we put on there?
The position vector between the two of them.
Yeah, a relative position vector between the two of them, and we could point that either direction, couldn't we? So let's say we're the observer here at B. Then we'd probably, if we're the observer here, then we're probably going to be keeping an eye on what A is doing. So we would be monitoring that position of A relative to position B. And you can now look at that picture and see that position vector A is made up of the sum of these other two vectors. And we've seen this before. Okay. But the position is not what we're talking about. What we're talking about is the velocity. So the position of A is equal to the position of B plus the position of A relative to B. And when we differentiate that, we get the velocity of A is equal to the velocity of B plus the velocity of A relative to B. However, we're on a rigid body now. So if you're the observer here at B and you're looking up here at A, what's A appear to be doing relative to you?
Not moving.
Well, let's see. What if I took this eraser and I'm the observer down here on this lower corner where my finger is, and I'm looking at the upper right corner? Is that not moving? Not right now. But what if I do this?
If you're standing on the object,
You're rotating.
I'm here. I'm not rotating with it. I'm standing here. I'm watching that other point. It appears to be in rotation, right? About me, about the observer. So this point appears to be, as I've said before, I don't like to use the colored chalk because it doesn't erase, or the colored marker because it doesn't erase well, but it's worth seeing here. This point appears to be in circular motion about the observer, which means that it's got a relative speed, doesn't it? What direction? And if this body had some omega, doesn't matter which way I put it on here. Let's say I put it counterclockwise to the left. Then how fast does that point A appear to be moving relative to the observer?
Omega.
Which way? Up here, right? With some velocity, relative velocity. So that has an apparent relative velocity. I'm going to erase this rigid body. This has an apparent relative velocity, velocity of A relative to point B, that appears to be in circular motion about the observer. But we know from the last class session that this can be written as what? In vector form. Omega cross R. So we have now that the velocity of A is equal to the velocity of B plus omega of that rigid body crossed with R of what? A relative to B. A relative to B. Here's the motion, here's the equation for that rigid body, its velocity. Okay, we've got time to do a problem. That's not too much development. Okay.
That's a stationary reference frame at B that is translated.
It's a non-rotating reference frame that moves with the observer.
Okay.
Okay? So we're just locked in using, say, traditional X and Y. We've got traditional X and Y, and we're just locked in. Everything we're writing in this equation is related to that X and Y. Okay? You know, tell you what, we're already on a roll here, differentiating. Why don't we go ahead and get to where we're going to be getting to with the acceleration? Why not? The book separates it into two fairly large sections, but we can go ahead and crank this derivative out, can't we? Right. Okay, let's do it. Go ahead. Okay. Go ahead and do it. You can do it. Okay, so don't look up here. I'm going to just go ahead and write it out, but just go ahead and keep writing out your derivatives, and then we'll see if we end up at the same place. Did you get the same result? Good.
Are you supposed to use parentheses? Or does it not matter?
It's implied.
It's implied.
Well, do you need parentheses over there?
No, because you know
No.
what way you have to do
Whether
it.
it dies or it doesn't die.
It die-
And it's kind of important if you want to drive it or not. So,
There's a lot of humor in engineering, as I keep saying. Omega cross omega is 0, so that
you have to
doesn't,
do
that
it the
doesn't
other
get you
way first.
anywhere. So that means you got to start there. Okay. Okay. Pretty cool. Not too tough. Okay, not too bad. And this is extremely powerful. This can be three-dimensional, folks. These equations, they don't have to be 2D at all. Matter of fact, oftentimes they're not. The stuff we're focusing on in this course is going to pretty much stick to 2 dimensions, but this mathematics can go into whatever dimensional realm you want to exist in. Okay, now, here's the important thing for you to grasp. Here's that rigid body. Here's A. Here's our observer, B. And where's that red marker? A appears to be in what kind of motion related to B? What kind of motion? Circular motion, right? So you might have some omega going on and some alpha non-zero on that rigid body. And so what you've got going on in these terms here, these last 2 terms, are the relative motion stuff. So what you want to keep clear in your mind on is that appears to be in circular motion. So there's going to be an R alpha type of term right there on acceleration, and a R omega squared term acceleration that way. Those are relative accelerations. And then you also, well, that's fine for the acceleration. That takes care of it. And back up here on this is that relative velocity, which is pointing up along here in the same direction as this R alpha. Okay? And look at the units here. R alpha, R omega squared. Okay. But those are relative terms to the observer. Okay. Very powerful stuff. Very useful. We could go back to every one of those problems on absolute motion and do them with this stuff, if we chose to. Okay. So I think we have time to maybe do one velocity problem.
okay, but if we go over
Or what, the whole world's going to explode, maybe, if we go over.
Huh?
If time runs out, is the whole world going to explode?
Yeah. No, we'll just pick it up next class session
No, I
if
was
we have
talking
to.
about
Yeah.
what he said. He said something about exploding.
Oh.
Apparently I missed it entirely.
Okay. Let's start with something straightforward. Here's one. This is the rolling wheel again. Wheel of radius r rolls without slipping and has an angular velocity omega. Write an expression for the velocity of point A in terms of theta and show that the velocities of A and B are perpendicular to one another. And I have to show you the picture associated with that, which is up at the top of the next page. Okay. So here's the picture associated with that problem. We're trying to show that the velocities of A and B are perpendicular to one another. And we want to write an expression for the velocity of point A. So the rolling wheel, and we've got an omega described as clockwise, similar to the way we developed the cycloid. Okay. Now we could do this using the absolute motion kind of approach if we chose to, but they want us to use the vector approach this time. So we know that the velocity of A is equal to the velocity of, let's see, what are we trying to do? We're trying to find
the velocity of point A in terms of theta.
Okay, so velocity of point A is what we're looking for. Okay, so suggestions on what to write. The what?
Point of origin is a couple.
Okay, do I need a point of origin? Look back over here at our governing equation. It does not. All we need is relative type of stuff. Okay. What part of this disk do we know? What part of this do we know something about?
Not slipping.
Okay, it's not slipping, so this is a momentary point at rest. Trying to find the velocity of point A. Description of that in terms of theta, not using absolute motion analysis, but using this vector approach.
So to like reference to our like two vectors that point to each of them, is that what you're
Yeah, well, I'm just trying to start writing something.
Let's start with the vector that starts from the very bottom point where it's at rest 2A, then 1 to B.
Okay.
Connect them.
Now, you're talking about position vectors?
Yes, position vectors.
Okay, and then we would have, if we did that, let's just without me writing, let me think about us doing that. If we wrote a position vector from here to A, here to B, and then from
B to A.
B towards A, and differentiate, the trouble is we don't know what's going on at either of those points. But here's a hint. Got it? Okay. Try this. Velocity of A equals the velocity of O plus omega cross R of A relative to O. What do you think about that? Is that going to help us any?
Step away, part of it there.
So you can figure out the velocity above.
And if we use a traditional defined X and Y to write our things that we may know, we don't know VA. Do we have any information about this?
Rotating at a constant speed, and it's going to be traveling at a constant speed in the X direction.
How fast is this? What is this? What's that speed?
2 meters per second.
You want to just leave point A as a velocity.
What's the speed of this center of the wheel?
That's the next
2 R omega.
So like R.
What did I hear?
Was it R omega?
R omega, isn't it? Don't forget the cycloid stuff we talked about, okay? The rolling wheel. The wheel is rolling down the road. You on your bicycle, that wheel, you're moving forward at a certain speed. The center of that wheel is moving forward at that same speed. So it's R omega. So this thing is moving at a speed of R omega. And so we have that VA is equal to R omega
That's going to be
in the X.
I hat plus omega is clockwise
So you can call it
into the board is
that's
Negative.
negative K. hat, right? So it's an omega, it's a negative omega k hat. Cross that with R of A relative to O. R of A relative to O. Be careful here. Very important, very important.
Sine theta, cosine theta, referring to that angle.
Okay, so you're going from here to there, folks. So be careful with that.
Negative.
Wouldn't it just be
Yeah.
Negative R sine theta. I. What about the J term?
Negative R cosine theta.
Okay, negative R cosine theta, J hat.
We're letting that, we firmly planted.
There it is.
The original coordinate system at the center of the wheel. If we wouldn't have to do one field added constants in it.
No, this is just a reference coordinate system, non-rotating reference coordinate system. So what we end up with now is the velocity of A. We combine, where are we going to get an I term over here on the cross product? K cross J. K cross J is going backwards, isn't it?
Yeah.
K comes out of the board at us. J is upward. K coming out, cross J is negative I. So that's a negative I times a negative negative stays negative. So we have an R omega and a negative R omega cosine theta I. And then K cross I is J. K out of the board towards you, crossed with I, right, is positive. K cross K towards you, crossed with I, is K. J. And so we end up with a product of our J term is negative, negative. It becomes positive, and we end up with a positive R omega sine theta
But isn't it negative?
J.
It's JK, which is the opposite.
K cross I.
Oh, K cross
K
I.
comes towards you.
Okay.
cross on?
Fingers in that direction, crossed with I,
Okay.
points positive J.
Or negative K cross negative I.
You can play the game, you can treat it negatively as well, as long as you're careful about it. You'll always end up with the correct thing if you do it right. And so the generalized expression then for the velocity of A is R omega factored out here, and we're left with a 1 minus cos theta being our I term, and then plus a sine theta J hat term. And why don't we, well, let's go ahead and finish this off. Did they give us prescribed values?
No, we're just doing it general.
Okay, we're just doing it in general. And so that's not the answer they had in the book.
They have 2 R omega sine of theta over 2.
Here's the answer that they get in the
Yeah,
book for the magnitude.
Oh,
For the magnitude.
Interesting. They didn't specify if you could have done a
Yeah.
vector format either too.
So if we want the magnitude of this, then we're going to end up with R omega, and then we need to figure out the magnitude of those terms in that vector. So we're going to have the square of this, which is 1 minus twice cosine theta plus cosine squared theta plus a sine squared theta,
Straight to the +1.
right? And then we have a 2
So it's going to be 2 minus 2
times
yeah.
1 minus cos theta left inside the radical.
You can actually
And if we would introduce a division of 2 here and turn this into a 1 minus cos theta, there's the identity in trig that we have, which is 1 minus cos twice x And that's equal to, is it cosine or sine?
It would be
Sine. This identity. And I believe that square root's inside the radical, isn't it? That 2? Yeah, inside the radical on the identity, yeah. And so you can transform this into that expression, and so then we would end up with their answer, which is twice r omega sine of theta over 2. For the velocity of A. And I think we have another, do we have another couple minutes left of time? Okay. The last part of this asked, show that these guys are perpendicular, or parallel to one another?
perpendicular.
That the velocity of A and B are perpendicular to one another?
Yeah, it just show that.
Oh, in their actual path, right? Because which way is this point really moving? You're tempted to say it's this way.
No, it's more upwards than that.
But what's happened physically to this point?
It's moving.
This piece of tread got lifted off the ground, didn't it? So this thing's really heading that way, isn't it? That point is really heading that direction, and this point over here is
going down like.
yeah, down, and it turns out, well,
They are perpendicular.
We can see
They
it's
said-
perpendicular. How can we show it though?
yeah, okay, so why don't we save that to ponder, and then we'll hit that the first thing in class, next class session. To show that those velocities are actually perpendicular to one another. Okay, that's it. Have a nice holiday weekend, too.